Hi, in this video we're going to take a look at hypothesis testing for two sample means. And in our previous sections we took a look at performing hypothesis tests for single samples, whether they be a hypothesis test for a single population mean or a hypothesis test for a single population proportion. In the next couple videos we're going to look at analyzing differences in means and proportions between two samples of data. So, in particular, we're going to examine whether there's a difference in means that is statistically significant. In other words, a difference in means between the first data group and a difference in means between the second data group that is considered statistically significant. Again, assuming that there's no difference in the means of each of the samples' population. So, to put it mathematically, if we denote our first sample as x, and then we denote our second sample as y, then we want to know if the difference in means between the two samples is zero. So in other words, the population mean for the first sample or first data group or data set x minus the population mean for the second data group y, is the difference between those population means zero. Or to put it another way, if the difference is zero, that would imply that the two population means would be equal to each other in order to have a difference of zero. So our null hypothesis is going to be the equality of the two data groups' population means. And then we'll look at our left-tailed, right-tailed, and two-tailed for our alternative hypothesis. But we'll be testing the equality of the two population means. So in this video, we're going to look at performing a hypothesis test on the mean for two dependent samples. And in the next part of this section, we'll take a look at independent samples. So recall from our discussions on probability that two events are dependent if the chance of the second event happening is affected by the first event happening. So in other words, the outcome of the second is affected by the outcome of the one happening right before it. And we're going to look at, for this part of the section, we're going to look at examples of data that's paired together in some way. Oftentimes having somewhat of a before and after theme, much like with experiments. So in other words, the two samples are dependent on each other because if we look at a before and after, typically it's a before and after for each individual subject within the data set. So this part for finding doing the hypothesis testing for dependent samples is sometimes known as a paired t-test. So we're pairing up like a before and after pair, or a matched pairs test. So depending on the statistics that you're learning from, they may call this either a paired t-test or a matched pairs test, or difference in means between two dependent samples. So unfortunately, we often have a lot of different ways of saying the same thing. All right, so for our paired t-test or our match pairs test, we're going to assume that the distribution and the differences of sample X and sample Y are normal. The test statistic, the t-test statistic, is found by taking the mean of the differences between the two samples. So the mean of the differences, here's our assumed population difference is zero. However, and we'll see this in the code that I created for this section, there's also going to be an option for testing whether or not the difference in population means is a particular value. So maybe not equal to each other necessarily, but maybe they have a difference of 10 or something to that effect. And then divided by our standard error, which is the standard deviation, sample standard deviation of the differences divided by the square root of the sample size. So here we have mean of the differences minus zero is just the mean of the differences. So we'll take the before minus the after, and that's our differences. And then we can take the mean of that list, the standard deviation of that list, and then n should be the same for both before and after for x and for y. We don't have any missing data there. So again, d bar represents the mean differences between the samples. So we got to take the mean of x, the mean of y, and subtract it, or we could take the differences and then find the mean of that. So our population difference for this section is going to be 0 for hypothesis testing. That's this value right here. However, please keep in mind that it is not outside the realm of possibility that we believe that there is a specific difference value. Maybe the difference value is 10, which then we could plug in for this part here. So, and then the code I have will allow for that to happen. S again represents the sample standard deviation of the differences, and there are n-1 degrees of freedom. So again, this is a t distribution, which is part of it is based on the degrees of freedom. All right, so example 1, a medication is given to patients in an attempt to lower their LDL cholesterol, the bad cholesterol. The tables below list the levels for maybe around 10 patients or so. At the 5% significance level, test the claim that the medicine is effective in lowering LDL cholesterol. So here we have subjects' cholesterol levels before and their cholesterol levels after. So notice, again, every single one of the befores has a paired up value for after. So again, that's why it's also known as the matched pairs. This is dependent because it does have the before and after effects. So for this one, our hypothesis, our null hypothesis, is that there is no difference in cholesterol levels from the before and the after. In other words, the mean of the before, population mean of the before, is going to equal the population of the mean after. And for this particular test, for the alternative hypothesis, we're testing whether or not the medicine is effective in lowering LDL cholesterol. So if it lowers it, that means that the before values would have to be greater than the after values in order for it to lower the cholesterol levels. So for the before to be greater than the after, that says that our population mean before is greater than our population mean after. This one's going to be a right-tailed test. So let's go to our code, which I will link this in the description. Don't worry about all this stuff. I tried to comment it, but I wanted to get this written rather quickly, so I didn't comment it too well, so please don't yell at me. But our significance level as a decimal is 0.05. The difference in population means we're saying that they're equal to each other, so the difference is 0. This is where I was saying you would have the option of saying a specific difference, maybe like 10 or so. So it's this line right here. But for this section, we'll just work with a difference of 0. The samples dependent or independent. They are dependent. We'll look at independent in the next video, so press option 1. This is a right-tailed test because we say that the mean of sample 1 is greater than the mean of sample 2. The population mean for sample 1 is greater than the population mean of sample 2. All right, now the data set, the fun crunching in the numbers here. So 95, 109, 127, 131, 117, 131. Okay, and we're done with that first data set. Hopefully I didn't make any errors. Next up, 91, 107, 129, 125, 110, 120, 97, 101, and 107. Okay. So our printout has some information that the mean sample difference is 4.333, so 4 1/3. Our sample standard deviation 5.3151. Sample size is 9. So again, with dependent, we should have the same number of elements in the first data set as we have in the second data set. Here we have our test statistic, our critical value, our p-value, and our one-sided confidence interval. In this case, our 95% lower bound. So these values are t-value 2.446. That is greater than our critical value of 1.86. So our 5% significance level for a right-tailed test with 8 degrees of freedom should give us 1.86 for its critical t-value. P-value 0.0201, 2.01%. Our alpha value is 5%. And our 95% lower bound is 1.0388, which does not contain 0. So it does not contain that hypothesized population difference of 0. You could get this lower bound also by constructing a regular 90% confidence interval, and the first value in your 90% confidence interval is 1.0388, which again will not contain hypothesized difference of 0. So all three of these approaches, the test statistic critical value approach, the p-value approach, and constructing a confidence interval, all lead to the same conclusion, to reject the null hypothesis. And again, we can see that the confidence interval will not contain the hypothesized difference of 0. So we are going to reject the null hypothesis and conclude that at the 5% level of significance, we're going to reject the null hypothesis that there is no difference in LDL cholesterol levels. So we can conclude that our sample suggests that the medication may be effective in lowering LDL cholesterol levels. Our results are statistically significant, where we can have a good enough reason to believe that they didn't just occur by chance. So, all right. That about does it for this video. Thank you for watching. I'll see you next time.